So we'll now look at Taylor polynomials for a very well-known function. And the first example that we will consider is the exponential function. Well, the exponential function is very nice in numerous aspects and also in terms of Taylor polynomials. So let's consider f and a equals 0. So we look at the Taylor polynomials in a equals 0. Well, what we do know is if we differentiate the function, regardless how many times we do it, we just get the exponential function back. So if we look at the nth order derivative in a for this function, then we obtain 1. Yeah, so this is a very special property for this function, and this holds for all orders of derivatives n. So now let's have a look at the Taylor polynomial. The Taylor polynomial is defined by this formula, right? So we get the Taylor polynomial in A, then we sum up over fa until the nth order derivative of f in A divided by n factorial times x minus a to the power n, right? Okay, now we just plug in the fact that we know that all our derivatives in A for a equals 0, that these are all 1. And also we can just simplify these terms x minus a is x. So if we do that, then we get 1 plus x squared divided by 2 plus x to the power 3 divided by 3 factorial, etc., until we get x to the power n divided by n factorial. And this is the Taylor polynomial for the exponential function. So other examples. So let's consider the trigonometric functions, the sine and the cosine of a function. The sine and cosine of as a function. So suppose we look at fx equals the sine of x, then we first calculate the derivatives, and although the derivatives are not always the same at a is 0, like for the exponential function, the derivatives follow a nice pattern as they are cyclical. Yeah, so let's see what this means. So f prime equals the cosine of x, then f double prime is of course minus the sine of x, and the third order derivative is the minus cosine of x. And if we take another time the derivative, then we get the fourth order derivative, which is again the function itself, right? And so from there on we see the same pattern developing, right? So we see the cyclical pattern in the derivatives. And this is nice, as for a equals 0, we get f0, f prime 0, etc. We can just summarize all these derivatives, and we can put them in a scheme and calculate the values. f0 is 0, f prime 0 is 1, f double prime 0 is again a sine of 0, so it's 0. The third order derivative is minus 1, as it is minus the cosine of 0. And then this pattern repeats, right? So we get here the f of 0, the f of f prime of 0, f double prime of 0, etc. Right? So this is a repetitive cyclical pattern. And now we can just determine the odd derivatives at 0, as these follow a certain sign, right? So if we have the first order derivative, I get 1, then minus 1, then 1, then minus 1, etc. So I get, as odd derivatives in 0, I get minus 1 to the power k. And also the even order derivatives are all 0, right? Okay, so this means that if I look at the Taylor polynomials of order 2 m plus 1, what do I get? I get I start with the first odd one, the other one vanishes, f of 0 is 0, so I start with f prime 0 times x, which would be just x, and then the second order derivative vanishes, so I don't have a term x squared. Instead, I have here minus 1 times x to the power 3 divided by 3 factorial, etc. So here you see the powers, only odd powers appearing in the Taylor polynomial for the sine. So we get this as a Taylor polynomial. For the cosine, we can do something similar, right? So just start collecting and calculating the derivatives. We see that we move from the derivative minus sine, then we get the second order derivative minus cosine, then we get a third order derivative, we get the sine of x, and then as a fourth order derivative we get the same function back. So this would be cosine of x, right? So again, also here we see, just as for the sine, we get a cyclical pattern, and now the derivatives I do a little bit faster. F0 is 1, f prime 0, which is a sine, will be a 0, just as the third order derivatives, right? So all odd order derivatives are 0, and the other ones, they follow the pattern 1 minus 1 1 minus 1, etc., right? So if we then look at um, uh, the uh, the the even order derivatives at 0, we get the following pattern. It's minus 1 to the power k, and the odd order derivatives are all 0 at 0. Okay, so this leaves us with t to n. So the even ordered Taylor polynomials are just given by or in x. They should not be 0, they should be in x. Let's change that. There should be an x. Then what we get is t2n in x equals 1 minus x squared divided by 2 factorial plus x to the power 4 divided by 4 factorial, etc., etc. So we can, and as a last element, we get minus 1 to the power n times x to the power 2n divided by 2n factorial. So as a final example, we will look at a natural logarithm, right? So fx is the ln of 1 plus x. And we're going to look at the Taylor polynomials at a equals 0. So if we take a derivative of this function, we get 1 over 1 plus x. If we take the second order derivative, this would be 1 plus x to the power minus 1. So we get minus 1 divided by 1 plus x to the power 2. And we may continue, right? So x to the third order derivative, we keep this exponent minus 2 goes up, right? So we get plus 2 divided by n plus x to the power 3. Yeah, do you see some irregularity here? We get as the kth order derivative of x, that we get minus 1 to the power k. So these signs keep flipping, right? So plus, minus, times k minus 1 factorial, right? Time divided by n plus x to the power k. That is the kth order derivative of this function. Okay, but now we want to have the Taylor polynomial in a equals 0. So what do we get? We get the f of a 0 plus f prime of 0 times x plus f double prime divided at 0 divided by 2 factorial times x squared, etc., etc., plus the final term is the nth order derivative in 0 divided by n factorial times x to the power n. Well, now just use the information that we put in here. So the f at 0 is 0, right? So the f prime at 0 is 1. So the f0 is 0. F prime at 0 is 1. So we get just x. And then the following term is x squared. And the x squared comes with the second order derivative divided by 2 factorial, which would be minus 1 divided by 1 divided by 2 factorial. So this is minus x squared divided by 2, and etc., etc. So we get, in the end, as a final term, we get minus 1 to the power n divided by n times x to the power n. Right? Since what we do is the last term would be to have the nth order derivative, and we get n minus 1 factorial, but we have to divide by n factorial, right? So we have to divide by n factorial. So what we do is n minus 1 factorial divided by n factorial is 1 over n. So again, we get a very nice um, uh, natural description of the Taylor polynomial for the natural logarithm, which has a lot of structure.